Okay, so today we're going to be doing an introduction to carbon compounds, right? So basically, I think we all know that in chemistry, we have two branches that are focused on the syllabus. Unit 1 deals with the inorganic chemistry, while for the most part, Unit 2 deals with organic chemistry, right? And the
Right.
main difference between the inorganic chemistry and organic chemistry is the fact that the organic compounds are carbon compounds, right? And this is based on the fact that carbon has a couple properties that I'll talk about later. Now, for all of you guys listening on YouTube, the classes are, well, this is our first class, so know that they have begun. I had on the poster that it would have started on September 1st, but I delayed a bit for a number of different reasons, which aren't very important for you. But it's $6,000 a month, and or if you're outside of Jamaica, it's 40 US dollars for the month, and you would get 2 1-hour sessions each week, which totals 8 hours for the month, and that includes your package will include recording of the sessions as well as practice questions and personal feedback from me, and basically personal coaching going up to your exams, so how to answer the questions and such. And there's a limited space available because I like to keep my classes small. So yeah. If you want to join the classes, you can contact me by WhatsApp or calling me on my cell at 876-501-1966. That's 876-501-1966. Or you can shoot me an email at younggenius.educate@gmail.com. That's younggenius.educate@gmail.com, or on Instagram at young_genius.official or _CAM_EO. My name is Cameo-Lee, by the way, and I'll be a facilitator for both chemistry unit 1 and unit 2. And for those who are following my page, you know that our Spanish CSET classes have begun, and our tutor Axania Morris is doing a fantastic job at the moment. So with that said, let's begin, shall we? All right, so first of all, I need you to know what these two properties are. So you have catenation, right? And tetravalency. So catenation is the ability for carbon atoms to bond to themselves, right? So here we have catenation, and it's the ability for carbon atoms to form bonds with themselves. So basically carbon to bond to carbon, and whether that may be straight chains like in the case of ethane I'm drawing here, or it can be branched chains like this. And I'll show you how to name carbon compounds later. Probably in this session, probably not, but depends on how far we get today. All right, Owen?
Yes, all right.
All right, and ringed structures. So a popular ring structure is your benzene ring, and ring structures can also include like cyclohexane, which is a 6-ring alkane. So 6 carbon rings. So 1, 2, 3, 4, 5, and 6. So each point here represents a carbon atom. All right.
Understood.
No, the other property is tetravalency. And this refers to the ability of carbon atoms to form 4 bonds, right? And I think I taught you how to look at prefixes last year and the suffixes. So tetra meaning 4 and valence. What are valence electrons?
Electrons that are on the outer shell.
Very good. So the outer shell. So tetravalency here literally means four electrons on the outer shell, right? So if we look at the basic atomic structure or atomic diagram that you learned to draw in grade 11, you'll see that carbon with 6 atoms, 6 electrons, sorry, 1, 2, 3, 4, 5, 6, would have four electrons on its outer shell, right? And it would be able to form 4 covalent bonds with another atom or other atoms or 4 other atoms, depending on what atom it actually bonds with. Clear? Then,
Clear. Understood. Following you so far.
great. Then you have like when you learn the electronic configuration using the S, 1s, 1s2, 2s2, then 2p2, right? Is that correct for carbon?
Yes, that's correct for carbon. That's correct.
Great. And if you look at the arrow and box, you look at it using the arrow and boxed method, you'd see 1s, this is our 2s, and this would be our p orbital, right? You also need to review the unit 1 stuff, right, Owen? So
Yes,
you're a
I'll
bit
be sure to do
sharper.
that.
So you're a bit sharper, right? No problem. So this would be your PX, this is your PY, this is your PZ. You're probably going to have extra classes with me, all right? 1, then you put the thingy, then you put this to fill it, and then you put in these singly, right? Now, if you notice in the p orbital, there is a bit of an anomaly here because this is completely blank, right? And carbon has the ability to form 4 bonds, right? Now, how is this possible, seeing that by Aufbau's principle, you have to fill the things first, right? Before you can actually pair them, right? You have to add them singly first before you can actually pair them. So this would be eligible for pairing, and this would be eligible for pairing, but this you can't put 2 electrons, right? You can't just drop in 2 electrons here. That would be going against Aufbau's principle. So in cases like this, atoms and especially carbon undergoes a process we call hybridization, right? I needed to pay attention to this part especially. So hybridization basically means the mixing of orbitals, right? So for like carbon to carbon single bond, you will have the orbitals, the s orbitals mixing with the p orbitals to form what we call degenerates. And these are hybrid orbitals, meaning that these degenerate orbitals have a lower energy than the p orbitals, but a higher energy than the s orbitals. So if we actually write the thing out, so 1s1, or just let's say 1s orbital, then above that would be the 2s orbital, then above that would be your 3p orbitals, right? And that would be a 2p. And we know that you have electrons here, you have 2 electrons here, and you have 2 in the p orbitals. All right. So for the carbon-carbon single bonds, you'll have the 2s orbital mixing with all 3 p orbitals to form what we call sp3 hybrids. And what this sp3 means is one s orbital mixing with three p orbitals. So basically one s to three p's. All right. So that would give you a total of.
Are you able to hear me?
Yes, I'm hearing you.
I don't know. Your screen is blurry, and I'm not sure. Not seeing it really well. And at times when you speak, you're breaking up for me, so I'm not sure what's happening.
You're sure your Wi-Fi connected properly? I said, you're sure your Wi-Fi connected properly? Like your net is up because, or it
I
could be
checked
my.
it a while ago. And like I moved from where I was, and
All right, so I think I fixed that problem. So let's continue. All right, so you're hearing me when I was telling you about the sp or 3 orbitals, right?
yes, I was hearing it. Therefore, yeah.
All right, great. So this is just basically means that you have one s orbital mixing with three p orbitals, right? And in that case, what you will end up with is four sp3 orbitals, right? And those will be your hybrid orbitals. So you'd have one sp3, a second sp3, a third sp3, and a fourth sp3, right? And each sp3 orbital will have a single electron that will cause you to be able to make those four bonds. So that's what happens with carbon-carbon single bonds. Now, these hybridized orbitals, or let's say hybrid for short, these form sigma bonds. While the unhybridized orbitals are the orbitals that will cause you to form your pi bonds. So I'm going to show you that now in the case of alkenes and alkynes. All right. So let's say you have C to C double bonds, right? What will happen is you have your 2s orbital, you have your 2p orbitals. The 2s orbital will only mix with 2p orbitals. So you will have 1, 2, 3 sp2 hybrids with a spin, and you will have these two p orbitals not being used anymore, and you'd have one free p orbital. So what will happen is you will see that for a double bond, you'll see that you have here, this would represent one sp2 orbital overlapping with another sp2 orbital to form a sigma bond. Because remember, that's how covalent bonds are formed, by the overlapping of orbitals, right? Then here you will have another. Remember, I'm looking at the chat, so if you have any questions, you can ask them there. And after the session, like the recording part for YouTube, I'll just go over a few stuff and let you go through your practice sheets and stuff that I have for you. So this other sigma bond here would be the overlap of another sp2 orbital and another sp2 orbital. Now here where we have the double bond, one of the double bonds is a sigma bond and the other one is a pi bond, right? So every double bond has one sigma bond and one pi bond, all right? So one of these would be the overlapping of two sp2 orbitals, hybrid, while one would be the overlapping of a free p orbital or unhybridized orbital, p orbital, right? So remember that pi bonds are formed by the overlapping of p orbitals, and those are the dumbbell-shaped orbitals. So when they overlap like this, remember they overlap laterally to form a pi bond, right? So laterally means they overlap side by side. So like this. So that's how your pi bonds are formed. So from the double bond, you have one sigma bond and one pi bond, and that's caused by you having sp2 hybrids or three sp2 hybrid orbitals and one free pi orbital, right? Now, in the case of alkynes, where you have C to C triple bonds, you have one sigma bond and two pi bonds. And this is as a result of sp hybrids. So you have your 2s orbital, and then you'd have your 3p orbitals. And as I said, you will have the mixing of this 2s orbital with only one of the p orbitals. So that could be the p, let's call it, say, the pz orbital. Remove one of those electrons. All right. So what you will have is 1, 2 sp orbitals. And if you're having trouble remembering if it should be 4 hybrids or 2 hybrids, the hybrids is the total number of orbitals. So like, as I said, you have 3p orbitals and 1 s orbital. That's a total of 4. So you know that you have 4 hybrids. Now over here, you have sp2 orbitals. So that's 2p orbitals and 1 s orbital. So that's a total of 3 hybrids. Now in this case, you have 1 s orbital and 1 p orbital. So that would leave you with 2 hybrids. Clear?
Yeah, I'm following you so far, yes.
All right, great.
So you're saying that basically it's like where you have the top one right there. It's
Which
kind of hard for me to see. The one that says 1 to 3.
the sp3
That
orbital.
one. Yeah, sp3 orbitals.
Mm-hmm.
Yeah, that one. sp3 orbitals. So that one basically works by doing what? 3, you're going to have like what? 4 orbitals basically.
4
But
hybrid
could you go over?
orbitals.
All right. Could you go over one more time, please?
Sure, no problem. So I was saying that, remember, hybrids are formed by the mixing of orbitals, right? So in order to form a sp3 orbital, what will happen is the 2s orbital here will mix with 3 of the p orbitals. That's the the px, the py, and the pz, right? Following?
Right, following.
Mm-hmm. So when that happens, what you'll get are sp3 hybrids. sp3 is basically a little code to tell you that there are 3 p orbitals mixed with 1 s orbital. All right. So you will get 4 sp3 hybrids. In the case of the double bonds here, you'll have a 2s orbital mixing with only 2 p orbitals, right? So in that case, you'll get sp2 hybrids. And what that means is 1 s orbital mixes with 2 p orbitals to form 3 hybrid orbitals. All right. And
Right, yeah.
for the triple bonds, you'll have the s orbital, the 2s orbital mixing with one of the p orbitals, and in this case, I said the pz, right? Which will give you an sp hybrid, which will really amount to two sp hybrids, right? That will have single electrons. And remember, I told you that the hybrid orbitals create sigma bonds. So you'll have the sigma bond forming and two free p orbitals forming pi bonds. So here you go for the triple bond. So in this case, 1, 2, 3 bonds. Did I tell you it was? Okay, yeah, it's correct. So in this case, we would have 1, 2, 3, and 1. Clear?
Clear so far, yes.
All right. So that still works out to four bonds. So this would be one sigma bond, and then one out of these three bonds would be another sigma bond. And then remember, you have two free p orbitals here. So two of the remaining bonds would be two pi bonds. All right. Okay, let's see. Yeah, I'll show you the diagram after class. All right. Another thing that happens with carbon compounds is a phenomenon called resonance. And you mostly see this in like the benzene or the ring structures, and we call those aryl compounds. All right, so in this case, you know that benzene has alternating double bonds. And so it can exist like this, or it can exist like this. So I hope you're seeing the difference. So in this case, that's why we usually represent like benzene with the circle in the middle, and this is called Kekule's structure. And it's called a resonant hybrid because of the fact that it can exist like this, and we're not really sure where the double bonds actually are in a compound like benzene. So in this case, the electrons are delocalized, meaning that they are spread throughout the compound. So that's why we represent it like a circle, right? In the case of V bonds here, the electrons are actually localized in one area. So in right around this area, concentrated area would be where the electrons are concentrated in the case of these compounds. Don't worry, I'm going to give you practice questions on explaining this hybridization thing, and you're also going to get a worksheet today. If we get to empirical formulas and stuff like formulae and stuff like that, you're going to get a worksheet on that as well. And I already have a worksheet ready for you for solving empirical formula and naming the compounds. You're going to definitely get a worksheet on that today. So get ready to work. All right, so let's talk a bit about homologous series and functional groups. All right, so for the homologous series, I think you should know this already, but I'm going over it again. Homologous series are a group of organic compounds with the same functional group. So there's a difference between what a homologous series is and the functional group. Now, the functional group is an atom or a group of atoms that give the compound its properties, right? So let's say you have the homologous series alkanes, right? And you know that's represented by the C to C single bonds. That's carbon to carbon, single bonds. The functional group would be the C to C double bond, while the homologous series, the series would be the alkanes. And the C to C double bond group is called the alkyl group, right? So whether that be methyl, ethyl, butyl, propyl, right? So that's what we have there. For the alkenes, that would be the homologous series, while the functional group would be the C to C double bond, which is the alkenyl group. Clear?
Clear so far, yeah.
So you also have alkynes, ALK-NES, which is the C to C triple bonds. You have the alcohols, ALCO, which are the OH, and that's the hydroxyl group. And remember, these all have general formulae. Aldehydes, and you have ketones as well. No, aldehydes, you can differentiate between them because you have the C to C double bond attached to a H, while for ketones, it's just the C to O double bond, right? And the C to O group is called the carbonyl group. All right, so this group here, the C double bond O, it's called the carbonyl group. So aldehydes are basically a carbonyl group attached to a hydrogen atom. So that's the difference between aldehydes and ketones, all right? Both have a carbonyl group, but aldehydes have an H attached to the carbonyl group, right? You also have amines, which have the NH2 group, usually drawn out like this. And you have, I think I forgot carboxylic acid, yeah. You have the carboxylic acid group, which is represented by COOH, and you know that you have the C double bond O attached to an OH, hydroxyl group for that. And of course, for your final bond, you'd have an R group, and you know the R group is whatever atom you're attached to that, all right? So there are characteristics of homologous series, and you need to know these. So I'm going to type them out later or later in the evening for you. So just listen right now. So it has a particular general formula, right? That's one characteristic. Each successive member increases by a CH2 unit, right? So what that means is, like, for methane, the formula for methane is CH4. And so what comes after ethane, that would increase by 1 carbon and 2 hydrogens. So ethane would be CH4 and 2, 6, right? And it's the same for propane, butane, and such. You add 1 carbon and 2 hydrogens. So for propane, it's C3H678. And for butane, you'd add 1 carbon to the propane, so C4, and 2 hydrogens. So 8 plus 2, 10. So C4H10. All right, so that's the second characteristic of the homologous series. Another is that with a homologous series, you'll find that they have similar chemical properties because they have the same functional groups. Now, this is telling you that with the same functional groups, having the same chemical properties will have them reacting almost the same, if not the same, as its other counterparts would in different scenarios, right? And remember, I told you that the functional group is the atom or the group of atoms that give the compound a particular or basically it tells them how to react, right? So it's the functional group of the molecule or the compound that actually tells it how it will react in a certain situation, whether you react it with alcohols, oxygen, or other chemicals. And the physical properties, on the other hand, they will change. They will change in a regular way. So like how when you were learning about periodicity on the periodic table, and you saw we're going down the halogens, the group 7 elements, you saw we're moving from fluorine to astatine. There were phase changes or changes of state in the compounds because fluorine, chlorine gases, right? Then we're going down to bromine. Bromine is liquid at room temperature. And then you have below that iodine and astatine, which are solids at room temperature. So for the case of organic compounds, let's talk about the alkanes. Start with methane, which is a gas. And as you go down, as in to methane, then propane, butane, pentane, stuff like that. I'll teach you the prefixes soon. You will see that there will be changes of state from gaseous state to liquid going down, and you get more dense as you go down. And as the chain gets longer, it basically, the properties or the physical property changes. So you can represent organic compounds by using their structural formulae, and the structural formulae are either displayed or condensed. All right. So basically, the displayed formula shows you exactly how the atoms in the structure are bonded. So for example, if we're supposed to take a look at ethane, right? This would be the displayed formula for ethane, because you can see every bond in ethane. And remember, this is one sigma bond, this is another sigma bond, this is another sigma bond, this is another sigma bond, sigma bond, sigma bond, sigma bond. Oh my God, it probably get annoying to hear me say sigma bond, but I wanted to remember this. So these sigma bonds are formed by hybridized orbitals, and seeing that they're single bonds, you know that these are sp3 hybrids. All right. I'm going to ask you a few questions to see if you get this. If you don't, I'm going to go over it for you. All right. So in the case of a condensed formula now, condensed formula is almost similar to the molecular formula. But the difference between the molecular formula and the condensed formula is, like, the condensed formula will show you how the molecule is drawn, while the molecular formula just shows you the makeup of the compound. So for ethane, the molecular formula would be C2H12345 6, which is actually CnH2n plus 2. What this means is, seeing that the carbon is 2, n is equal to 2, ethane would be C2H2 times 2 plus 2, which is 4 plus 2, which is 6, right? So that's how we got the molecular formula for ethane. And now for the condensed formula, what you want to do is show the carbon atoms and what atoms are bonded to it. So you'd write CH3, because on one carbon atom here, there are 1, 2, 3 hydrogen atoms bonded to the first carbon atom. Then to the other carbon atom, you'll have another carbon. So this is showing you that you have another carbon, and on this carbon, you have 3 hydrogens as well. So let's look at the displayed formula for, let's say, a bromoalkane. So let's say you have this put a BR right here. H, 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 and H. You write here the first carbon, and on that carbon you have 1, 2, 3 hydrogens. Then you have another carbon, and you have 1 hydrogen. So you write down H, 1 bromine. So you write Br. Then another carbon, so C, and 1, 2, 3 hydrogens. So H3. So that would be a condensed formula for this compound right here. As per naming it, this would be 2-bromopropane. But I'll tell you how to show you how to name them later.
Wait, this was the what we did first was the molecular. This is now the
Condensed.
condensed.
Yeah, I'm going to do more examples. All right, let's go again. I probably took that off too fast. All right, let's say you have C, 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 H, 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 H. This is propane. H, H, H. Right? This is the displayed formula. So it shows all the bonds that are formed, right? And you'll realize that each stroke represents 1 sigma bond, or one bond between carbon and another atom. And remember, carbon always has 4 bonds. So if you count 1, 2, 3, 4 to this carbon atom, there is also 1, 2, 3, 4 for this carbon atom, and 1, 2, 3, 4 for this carbon atom. All right. So you can tell that that's correct. You can also use this to check if your answers are correct sometimes. Later on in the whole chemistry thing, when we start doing other questions, I'll show you how you can actually check your answers if they're correct. Because some answers that you'll get, especially when you're doing combustion analysis, is just not possible, given that carbon has to have 4 bonds with it, and sometimes you'll get 5, so you can attach 5 hydrogen atoms to 1 carbon. It has to be 4 if you're going to do something like methane, while if you're going to do like carbon to carbon, you can have 4 hydrogens attached to 1 carbon, because where's the other carbon going to go? So you'll see it, trust me, you'll see it. So in this case, this is the displayed formula. Now for the molecular, remember the molecular just shows you the makeup. So basically how many carbons, how many hydrogens, how many bromine, how many chlorine, fluorine. So here we go. Or oxygen, it depends on whatever you put. So here we have 3 carbons, so C3, 1, 2, 3. H, and you count how many H's? 1, 2, 3, 4, 5, 6, 7, 8. So 8 H's, and that's your molecular formula. And that's it for your molecular formula. Now for the condensed formula, you are going to show how everything is bonded. So on your first carbon atom, you have 3 hydrogens. 1, 2, 3, right? So H3. For your second carbon, how many hydrogens are bonded to the second carbon?
2 hydrogen atoms are bonded to it.
Very good. And for your third carbon, you have 3 hydrogen. So that's your condensed formula. I'm going to let you try one.
Oh, okay. I think I'm getting it. Yeah.
We'll see. Let me see. So suppose I give you this one, right? And I don't want to be lazy, but I really don't want to write all the H's, but I'll write them. All right, so tell me,
I know the feeling.
what would be the condensed formula for this displayed formula shown here?
The condensed formula would be CH3, CH2,
Very good.
CH2, CH3.
Great. What would be the
Oh.
molecular formula? I'm a rocket science.
What is this? 4,4,10. C4H10.
Very good. And just like that, you got it. All right, let's give you another one. I'll give Anisha some when she comes in the next class to test. Not really test, but to ensure that she gets it. All right, suppose me do this to you and say, you need to tell me the condensed formula. I'm writing super bad today, but please stay with me. I'm extremely tired. All right, condensed formula, miss. Oh,
All right, CH3. No, I'm here.
okay.
CH3.
Mm-hmm.
CHBR. Is that
Don't
how
ask
it's
me,
said?
tell me.
All right, CHBR,
Mm-hmm.
and then CH3.
Very good. So, I think I got in the hang of that. No. What if CXC go take them wicked self and give you a branched um compound? So let's say they give you something like this. And I'm going to show you later why a branch is never placed on the first carbon. Branch is never placed on the first carbon. Remember that. If you see, if it look like a branch, it's tricking you. It's not a branch. If it's on the first carbon, it's the chain continuing. And I'm going to show you examples like that.
Noted.
All right. Let me do a little tracing here. Whenever you're naming the compound, you want to find the longest carbon chain first. So you want to think of it like a rope, and a rope has the ability to bend, right? It can curve, but it's the same rope. It can bend like that. It's the same rope. It can go straight. It's the same rope. It's not disconnected. You want to think about these carbon chains like this, right? In this case, the longest chain would be 3 carbons no matter where you go. If you go this way, it's 3 carbons. If you go this way and the rope happens to bend, it's still 1, 2, 3 carbons. In some cases, you'll have a bend like this, and it's actually 5, 6, 7, 8, 9, 10 carbons. And you will think it's either an ethyl group branch or a methyl or even a propyl, right? It's not a branch. It's the chain continuing, right? And in this case, this would be your branch, but I won't use this as the example because, as I said, no matter where you go, the carbon chain is still 3 carbons long, okay? So in this case, the condensed formula would be here. You have the first carbon, you have 3 hydrogens, then you have another carbon, you have 1 hydrogen, and in brackets, you're going to put CH3 because it's a branch, right? So you place your branches in brackets, and then your next carbon bonded to this carbon would be H3, right? I'm going to do another one.
Everything on the board? I didn't see. Oh, it just came up. Sorry.
All right, let me give you a few seconds to digest that.
How it works, it's like what? The first carbon is bonded, so it's CH3. Then the second carbon now, that would bond it to another carbon, but it's just written as CH. And then in bracket now, you continue with because it's bonded to that carbon, that hydrogen atom down there, so it's now CH3. And then now the last carbon, okay, I think I'm seeing something. I think I'm seeing the pattern.
Okay, let's try another one. Yeah, I'm not going to use these PowerPoints. I'm seeing a bit of a fault with them, and it's kind of annoying me. So I'm going to reconstruct my design and come again. All right, let's say I give you this one. right? And you put, I don't want to shortcut this thing, you know. All right. Let's say I put the branch right there. The branch is right here. And I put H's on the rest of these, right? H, 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 and H. Now, the first carbon has 3 hydrogens and another carbon bonded to it. So you want to keep that in mind. You know? This carbon is bonded to 3 hydrogens and another carbon. So that's how you're continuing the chain. This carbon number 2 is bonded to 2 hydrogen atoms and another carbon atom. This carbon atom here would be a third carbon, is bonded to 1 hydrogen atom. Then it has a chain. It has a branch, sorry. So you want to put that branch, represent that branch in brackets. So branches are represented in brackets, right? And then you want to say the other bonded to the other carbon compound, H3. Clear?
Clear.
All right, so let's say I give you this one. Let me give you something short. Let me clear off everything, because, all right, H, C, 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 C. Oh, okay. Yeah. All right, let's try that one.
Wait, important question before I begin this. Why is that find the longest chain important again?
It's when you're naming the carbon, whenever you're naming organic compound, you find the longest chain first. So in this case, 1, 2, 3, 4, this wouldn't be propane, this wouldn't be a branched propane compound, but it would be actually a branched 1, 2, 3, 4 butane. So this would be the branch right here. So it would be 1, 2, 1, 2, 2 methyl, 1, 2, 3, 4 butane. And it would not be 1, 2, 3, it would not be 2 ethyl propane. All right, it would be 2 methyl, because that's a methyl group, CH3.
How you know it's a methyl?
All right, CH3 methyl, C2H, I think it's 5, yes, is ethyl. So it's going to increase by the CH2 unit. So for propyl, it would be C3H567. Right. I guess you're going to have to study these, but after doing practice with them, you're going to remember them. Trust me. You're going to remember them. Don't worry about it. You're going to remember them. Just give it a little time. All right.
But repeat those names. So CH3 is called methyl. And what is C2H5 called?
All right. Say two carbon atoms, ethyl. Remember, these are the alkyl groups.
Oh, that's what you're using. Okay, all right.
Yeah. And then the 3 would be propyl or propyl.
Yeah.
Then 4 butyl, 5 pentyl, hexyl, heptyl, octyl, nonyl, decyl. That's so nasty.
Yes, very much so.
Yeah.
Wait, you keep on say actyl, right? That means alkenes.
Remember this,
That means
the single bond, carbon single bond. Remember the group is called the homologous series are alkanes, right?
And the functional group is called yeah, that.
Yeah.
Because I don't really know all them by heart, so sorry if I keep asking again.
That's why you're here. But yeah, tell me sorry for. Don't tell me sorry, miss. That's not how we
All
roll.
right, with the methyl, it's methyl, right? Methyl, that's
Methyl.
like
Methyle. Methyl. Or methyl.
okay, methyl. Oh, so it's just the tile,
Mm-hmm.
the wild part.
The YL. The YL.
So and then it's ethyl, propyl, butyl, pentyl, hexyl,
Or hexyl.
yeah, hexyl, heptyl,
Heptyl.
octyl,
Octane.
non octyl, yeah, thanks, octyl. How this go? Not
I think it's nonyl.
nolil, thanks. And and
Decyl.
decil,
Decyl.
decal. Yeah, all right,
Decyl.
thanks.
I've never seen one like that though. That just sounds like one stretch. I think
Okay. Oh,
like there's an idea in my head why I've never seen one like that, and it's the same reason for the the chains, because they're not going to get they don't give chains that long. I think that's why I've never seen one like that, because the actual carbon chain will have to be longer than the branch. That
oh,
sounds funny, but that's the main thing I was trying to show you here. That's why I was
oh.
telling you that this is not two ethyl, because 1 2, right? This would, if you call this the branch, you'd think this is an ethyl group, right? C2H5, right? You would think that this would be two ethyl propane, right? But the longest carbon chain is actually 1 2 3 4 carbons long, and not 3 carbons long. You see? So the branch
Yeah, I
now,
can see that. I can say I see that it is going down. It can
yeah,
is it on the first carbon? It's on the second carbon. It's going down,
yeah.
and then now on the second carbon we have in total with the no wait there. So how is it? How is that you get the fat? Wait there. How is that you get? How is that you know how much hydrogens you're working with?
How many hydrogens you're working with?
Yeah, like CH3, like how when I see like a branch like this branch structure,
This
right?
is not a branch. That's what I'm trying to tell you. This right here, not a
Uh-huh.
branch. It's not a
What
branch.
is it then? What
Remember,
is
I'm
it
telling
then?
you that. Ooh, think of it like a row. You're trying to find the longest carbon chain, which is the most the one with the most carbons when you continue counting, right? If you count from here, 1 2 3, right? This is only 3 carbons. If you consider the chain going this way. Now, if you consider the chain going this way, ooh, this is 1 2 3 4. So this is your longest
Oh, so
carbon
chains
chain.
can go down. I thought chains could only be straight.
Yeah, that's what I want
Yeah.
you to really recognize.
Oh, okay, I get
Chains
something
aren't
now.
always straight. That's why I use the rope analogy, because I'm telling you, if you have a rope, right? If the rope is straight,
Yeah,
it's the same rope. If the rope bends, it's the same rope. If the rope is
true,
in a
true.
circle, it's the same, or
Same.
spiral, it's the
True.
same rope, as long as
So
it's connected.
how do branch compounds look then? That's interesting.
This is actually a branched compound. The branch, though, is a methyl branch and not a ethyl. That's what I'm trying to tell you. Most people would mistake this for an ethyl branch and call this 2 ethyl, propane. But this compound is actually 2-methyl butane.
Alright. Other part I'm gonna get now.
All right. So here you have, oh my God. All right, let's draw this over. And you know what? Let me get off this and go to my trusty old whiteboard. Why did I discard? Whiteboard. I think I didn't clean the whiteboard the last time I used it. All right. You know how this thing go? Pick your color, any color.
Purple.
Purple, great. All right, let's use the dotted. You know, I like to use the dots. All right, so let's draw the compound. 1, 2, 3, 4. Lies, it was 3 carbons. And I had put the chain here. 1, the brand, 2, right?
Put it on the second carbon here.
It's not a branch. I'm
Not
going
a branch, that's a
I'm
branch.
going to explain to you now why it's not a branch. Look at me teaching you to name compounds before I actually wanted to. All right. This look kind of jumbled, but I hope you can follow. All right. Now, whenever you're naming compounds, you want to find the longest chain. If you consider this as a chain, that's only 3 carbons, right?
Yeah, going across, that's only 3.
But you can turn this way and you get 4 carbons. So which would be the longest chain?
The one where you turn and go down.
Exactly. So this is the longest chain with 1, 2, 3, 4 carbons. Now, this therefore has to be a branch. Clear?
Clear.
All right.
Wait, other part is a branch? The part then green
Yeah.
a branch part?
The part that I just circled would have to be the
Yeah.
branch because it's not a part of the longest chain.
Oh, so branches work.
Yes.
Alright.
Yes, that's
I'm
what
sorry,
they call
Mr.
the
Dunn.
branches. It's like a tree. You have you have your main trunk and then you have your branch.
Sorry, we just done. We just done. So
No,
sorry, we
man.
just done.
A lot of people. I made the mistake the first time I did a test. I think the majority of my class made the same mistake. So here we go. So it's like a tree. You have your main branch and then you have your main trunk, right? That's what they're called, right?
Yes.
You have your branch going out from it. So that's what you want to think about. Your main branch or your main trunk is your longest chain, and your branches are your little twigs that go out from it that aren't a part of the main branch, right?
The main chain, yes. The main branch, yes.
So the main chain is the 4 carbon chain, right? Which is the longest chain. Remember, your main chain is your longest chain. So the one with 4 carbons is longer than 3 carbons. And that's why that's not the 3 carbon way would not be a main chain. Get that? So seeing that this 1, 2, 3, 4, you know that it's butane because it's actually 4 carbons, all carbon, single bond. So you know that the homologous series is an alkane, right? I feel like you're not there. But
I'm
you
here,
are
but we
there.
just moved my location because my internet get unstable. So I load again.
Okay. So again, driving the point across, that's butane because it's 4 carbons long and it's carbon to carbon, all carbon to carbon single bonds, right? So it's an alkane. Now, whenever you're talking about your branches now, you want to identify your branch first. And since that we identified that this isn't part of the main chain, then it would be a methyl group. So it goes in front.
Oh, so now me get it because it have a CH3 upon it. This becomes the methyl group.
Yep.
Oh, alright. Wait,
And
this
the two.
where two come from?
The 2 is because it's on the second carbon. So you count again 1, 2. You could also count from this way 1, 2, 3, but you want to use the smallest number, the
Oh,
smaller
so I
number.
get this now. We put two. We use two. Oh, sorry. Finish first.
All right, so we can count from this way 1, 2, and it's on the second carbon. you might ask why we never count from the other way, right? If we count from the other way, 1, 2, 3, you get 3, right? You want to use the smaller of whichever two numbers you get whenever you're counting from the directions, right? If you count from this way, starting from this way, we got 2. And counting from this way, we got 3. So what you want to do is use the 2 because 2 is smaller than 3. Clear?
Show me that one more time, please.
No problem. No problem. All right. So I think it got a bit messy. Let's do the drawing over again. Let's redraw this, not taking into account 1, 2, 3, go down 1, 2. All right, so it won't be too jumbled. I'm just going to write it like this, okay?
Yeah, man, that's okay.
All right, then you have an H there and actually you have 3 H's over here. All right, great. So that's what we're working with. Now we identified that this here would be our longest chain, right?
Yes, true.
Now counting the carbon atoms from this direction, 1, 2, we meet up on the branch on the second carbon, right?
That's true, yeah.
And if we count from this direction, we meet up on the branch at the third carbon. You see that?
Yeah, me see that now, yeah.
But whenever you're naming compounds, you want to use the smaller numbers. So that's why we're going to say that the branch is actually in position 2 instead of position 3.
Okay, I get it now.
Yeah.
All right.
So this.
Oh, finish what you have first. Let me continue.
So this 2, right? It's just telling you the position of the methyl group on the butane, on the butane compound, right?
Interesting. All right.
You want to
So
try
wait,
one?
so the 2, but wait, so the 2 indicates the location of the methyl group?
Yeah, the branch.
Of the branch, yeah. Sorry, yes, of the branch. So
This is still the
question.
methyl group. Yeah, question.
Question. Alright, on the chain now, alright, like this number, it can be any number, right? It can be 1, 2, 3, 4, right? Alright,
Wait,
no.
wait. Let me not just say like that. Explain yourself.
Like it can be just a number. Like I'm not really sure, I'm not really getting into specific because I'm not really specific about it, but it can be a number, right? The question is, will it always be on the chain?
Wait, what? Will
The
what
question,
always be on the chain?
the number to identify. Like, is it always supposed to be on the chain?
It's you count on the longest chain.
Oh, you always count on the longest chain. All right.
Yeah.
And then no, the thing with it now, when you count and find that number is supposed to be up the group basically. For example, in the case, suppose it's another methyl group. The methyl group will always be as a branch on that chain, on the main chain.
Let me see. You're asking me if I were supposed to put the methyl group on another carbon atom.
Yeah, another carbon atom. So it wouldn't be up there. The branch wouldn't be up there anymore. It would be like, so for example, it would be like on the second carbon down here. Well, it'll be on the third carbon. Yeah.
All right, so let me move it. If I put the methyl group, I have to remove one of these hydrogens.
And you put it on the CH2. And you put it on the CH2 part, right?
You have to remove one of the hydrogens, ON, remember, because carbon only has room for 4 bonds. All right.
Yeah,
So
sorry.
Stop saying sorry. I come back with the sorry this year again, girl.
I'll try it again.
Don't worry about it. Here is where you make the mistakes, not on the exam paper. Don't harsh, but it's true. All right. So if you put it here now, you can count 1, 2, 3. If you count from this direction, 1, 2. So it's still on the second carbon. So it would still be 2 methyl butane. You see that?
Me think so, yeah. Me think so.
You always use a smaller number. You want to try one?
Oh, yeah, we can try one, yeah.
Why did I use the one in the book? Like, I'm looking now in the book and I realized that the example that I used is in the book. So now I have to make up one. I thought I made up one. Bruh. All right. No worries. I have one for you. I'm not actually counting. Let's see. Trying to do this as neat as possible so you don't get confused. You can draw it out in your book first and work it out in your head and then tell me, okay? Try naming this compound. Remember, identify the longest carbon chain first, and then I think it's going to look funny. Don't worry. I know you're going to have a hiccup, but whatever you're thinking is correct. I'll just tell you that from now. Just assume whatever you're thinking whenever you look at it and identify the longest chain is correct. All right? Just do that and answer the question. So a bit risky, but I have faith in you. If you're wrong, no problem.
Repeat.
It's going whenever you're trying to identify the longest chain in this one, it's going to look funny. Don't worry about it. Whatever you're thinking is correct. It's so risky for me to tell you whatever you're thinking is correct, but don't worry about it. Just try. Identify the compound. Identify the longest chain first, then identify if it's the homologous series, right? And then identify the branch, then put it all together. Remember, the number tells you the position of the branch.
Do that over again. Make sure so me have it down on paper. Can't guide as one guy. This is the
Okay.
branch. It's something with this.
Identify the longest chain first. Right?
Yeah. Have that. Yeah.
After you identify the longest chain, figure out if it's an alkane, an alkene, an alkyne, haloalkane, carboxylic acid, whatever. Right? Identify the homologous series. Right? How you're going to identify the homologous series? Look for the functional group. Right?
Yeah.
Then identify whether the compound has a branch or not. Continue. Right. If it has a branch, if it has a branch, remember the number identifies the position of the branch. And remember, you use a smaller number from whichever direction you go to come from. So if you come from the left first and you get a bigger number than if you came from the right or up or down, then you use the smaller number. You understand what I just said?
I understand what you just said, man.
All right, great. So try naming this one and let me take your time. No rush.
Longest chain, the homologous series. Then if you have one, then you identify if you have one branch. If it has a branch, make sure to remember the number. All right. Identify the number for finding position.
No.
Is this?
You got it?
Yeah. Okay. Is this methyl butane?
Yeah, it is. But isn't that what we just did though?
Yeah, we just did a while ago. Like, if you look funny, you know, because the thing is, we could have either go across or we could have go down. We could have the chain could have just continue straight along or we could have go down though. It wouldn't really matter. It'll have go down still. It wouldn't just like get the same result.
Yes, that's true. That is true. All right, let's say.
Like, you know, so I feel nice because like when we reach my grade level, we get you know like me feel so done because like they on the board and everybody else answering and me no not one. Just God, just. Anyway, besides the point, let's continue.
Okay, what if I added? What would this be?
For recording, Cameo.
Oh, let me pause while you try to get that. All right, go ahead.
Is this 3-methyl pentane?
3 what?
3-methyl pentane.
1, 2, 3. Yes. I need to work out these things before, before I
You know, they love methyl. They ever do anything that's different?
Yes, miss, they give you something,
Yeah,
miss.
thank you. Sorry, I'm being done again. I forget you said you can't have double. You can't double bond between carbon atoms.
Yes, miss. They give you something. I'm just starting you off easy.
Yes, I appreciate that.
I don't want to throw you in the deep end to drown. That sounded morbid. What would this be? I'm not pausing. Work your brain a little faster. A joke. Here, a joke. But I'm really not pausing. Can't bother. Take your time. Don't rush it. Take your time and ensure that the answer is correct. Okay?
Come, so
Mhm.
I'm still seeing it in there, right? But no, it's like they give me two different. No, let me see one meet. Let me get one methyl group somewhere along the way. But then me gonna have this. Me gonna have this atom. Me gonna have this other part. What's it? CH2. That part there. I don't know what to do with that part.
Okay.
So me can figure it out. Me gonna
Okay.
try.
Okay. Just tell me if you're having any trouble. And remember, you need to ask me specific questions, all right? Same, that's how you answer your questions. Be specific and ask me specific questions. Say, I get this, but I don't get this part, okay? Remember
Yes,
that.
I remember that. Yes.
We started at 7:30.
Yeah. Mm-hmm.
I'm going to cut the recording at sometime soon, but that doesn't necessarily mean that we'll end now. We're ending when you get this.
Yeah, man. Me know. Alright, to be honest, I'm seeing that, and I know for sure well, I know that the homologous series is alkane for sure, and I know that the longest chain has what 5 carbons, because it doesn't matter if you are to go down or across, you're going to still see 5 carbons.
Exactly.
So I know for sure that it's pentane. However, where I'm getting messed up is I'm seeing CH2 and I'm seeing CH3.
H3.
I
So if
don't
you've
know.
after you identify the longest chain, Owen, what do you identify next?
I identify the brands. I know that's
Exactly.
what. Yeah, and I'm seeing like basically two. I'm
So
basically like
CH2, CH3, that's a branch. Which
CH2.
branch is
Yes,
it? It's not methyl, because methyl is CH3. And that has increased by a CH2 unit. So,
oh, so it's C2H5.
yes, ma'am.
Is it ethyl? Is it
What?
so? How
Methyl?
do we is yeah C yeah C cause something two. Is it ethyl? That
Yes,
would be
miss.
great. Good. I'm following. I'm getting on track. Oh, sorry.
Take your time. Take your time.
So now there would be 3 ethyl pentane.
Very good. So I'm going to give you more to practice, okay? Let me cut the recording.